There is one more question, that is, any specific ports is used for leaky wave, sir?
No, that will depend on which type of structure you are using. So let's say if you are using a microstrip line, basic transmission line, so just use microstrip, what you use in microstrip simulation. If you are using like SIW, so use the same port, and that will depend on a structure.
So I think these
Okay.
were the questions. Those were from the previous lecture.
Session.
So now we can start the current.
Okay. Okay. So welcome back to the next session. So in this session, we have our speaker, Dr. Saurabh Kumar. He is one of the coordinator of this course. So he will be talking on miniaturized antenna using materials. So before handing over this session to Dr. Saurabh, let me introduce briefly him. So Dr. Saurabh received his PhD degree in RF and microwave engineering from IIIT Jabalpur in 2017. He is a silver medalist in PhD degree and gold medalist in MTech degree. Currently, Dr. Saurabh is working as an assistant professor in the Department of Electronics and Communication Engineering, NIT Hamirpur, Himachal Pradesh, since 2018. Prior to joining NIT Hamirpur, he worked as an assistant professor in the Department of Electronics and Communication Engineering, NIT Andhra Pradesh. He has more than 8 years of experience in teaching and research. He has co-authored more than 25 papers in referred journals and conferences. His research interests includes planar and microstrip patch antennas, artificial materials like metamaterials, electromagnetic field theory, RF and microwave engineering, and nanophotonics and plasmonics, etc. So with this brief introduction, I would like to invite Dr. Saurabh to start this session. Thank you.
Thank you, Dr. Prasad. Kindly let me know whether my screen is visible or not, as I will not be able to see you all. So as I am with the full screen, my
Yes,
voice is clear to all.
yes, yes.
Okay. So good noon, each and everyone present here. So today the discussion will be on the miniaturization techniques and their challenges. So in this GIAN course, we will be having the following the outline of this particular talk. That will start with some introduction. Then we will discuss that why the miniaturization is required, and then we will be moving towards that fundamental limits of electrically small antenna. Then some miniaturization techniques, those are available in the literature. I will be discussing those things with the basics as well as with the modern miniaturization techniques. And then we will be discussing the some research carried out in our group, and then we will be doing a comparative of it, and then we will be finding that what are the potential and the limitation of the different techniques. So before moving into the techniques, we will be discussing the antenna miniaturization. So first, you should know that what is the antenna, as it was discussed already in the previous lecture also. So just to give a brief, that antenna is nothing but it can be a metallic rod or wire or any planar form that is used to radiate and receive the radio waves. Or IEEE definition will be that antenna or aerial as is a means for radiating and receiving the radio waves. The microstrip antenna is one second. The microstrip antenna is nothing but it is a metallic patch that is seated over the grounded dielectric substrate, and this substrate can have the epsilon value that should be some lesser one, so that you will not be having any accumulation of the electric charge. Uh, this patch can have any shape. It can be of rectangle, thin strip of dipole, circular, or elliptical, triangular, or any other configuration you can take depending on your requirement. Now, why we are discussing the microstrip antenna or the planar antenna? Because I will be mostly discussing the technique of miniaturization. Those are applicable to the planar one. The designs, those I will be showing to you. However, you can apply the technique to the other non-planar antennas also. So the microstrip antenna is in itself is having some advantages over the other antennas, like it is a low profile. The third dimension is too small as compared to the three-dimensional antennas. The low cross polarization radiation will be there. And I am thinking that all the participants here are having some basic knowledge of the antenna engineering and the electromagnetic theory. So they will be knowing that what is the polarization, conformability, and all these things. And simple and inexpensive to fabricate using the modern printed circuit technology. And it can be the mechanically robust and can be compatible with the MMIC circuits, and it can be mounted over the high performance aircraft, spacecraft, or any other device. So the conformability there will be there. Then some major operational disadvantages are it will be having the low efficiency, low power, high quality factor, poor polarization purity, poor scan performance, spurious feed radiation, and very narrow bandwidth because of the low profile and the smaller dimension. And as the radiator is small, so you will be feeling that the antenna is, as compared to the three-dimensional or the horn antenna, it will be having low efficiency because it is using some dielectric constant, some dielectric substrate is used. It will be handling the low power, high quality factor will be there. The polarization for which it is meant to radiate is not that much pure as compared to the other one. And then scan performance is also less. And depending on the feed, you will be having the different spurious radiation from the feed can come. Like if you are having the microstrip or if the substrate thickness is high, so then you can have a feed radiation that is coming from the inner probe of the of the coaxial feed, and the narrow bandwidth will be the issue for this planar antenna. Now, why miniaturization? Why it is required? As you know that this is the world of the miniaturization. The device size is compact, or one can say that the mobile phones are now not the compact one as you find in the previous mobile. Those were of the keypad with the keypad, so they were in the small dimension. But this particular thing, that world of the miniaturization, means as the number of the technologies are coming into the same platform, means the display you need and the number of the sensors you need and each and everything you need over the limited space, and the antenna portion you will be having the limited there. So the size of the device is limited in terms of the antenna placement. That requires the development of the electrically small antenna. I have just given the example of the one like your mobile phone. It is not fixed that you will be having the requirement in the mobile phone. You will be, each and every device is having the minimal requirement. So the development of electrically small and the low profile antenna for both the civilians and defense application is required. So microstrip antenna is a good candidate that can come into the picture, and it can resolve the things like it will be taking a lower third dimension or low profile it is, and it can be used in the spaces where the size requirement is limited. However, the further size reduction is also required in some applications. So the miniaturization is a topic of interest, you can say. So now what are the limitations of electrically small antenna? So if you are designing a electrically small antenna that is less than the lambda by 2, you can say. The ordinary, if you will discuss that, there will be some antenna that will be depending on the operating wavelength. So if you are taking lambda by 2 half wavelength dipole and you are doing with some miniaturization of it, so then it will be less than that. Electrically small, less than lambda by 2 if it is. So what will happen if you are designing a smaller antenna that is electrically small, means the electrical dimension is too small, electrical dimension in terms of wavelength. So it will be losing its radiation performance. And how the radiation performance are reduced? with the increment in the quality factor, the efficiency as well as the bandwidth of the antenna will also reduce. So these are the three major factors. Those are degrading the antenna performance. Not limited to these three. There are the other. There can be the, depending on the technique to technique, the antenna can have the different radiation pattern. It can deviate from its original radiation pattern if you are doing so. But I am not at this particular slide. I am not giving that factor into the picture. So if you will come with the quality factor, and you can see from here that quality factor of an antenna, that is the radiation quality factor, is generally accepted with this equation, that is dealing with the 2 times of the operating angle frequency, WE divided by P radiated, where WE and the WM are the electric and the magnetic stored energy, and the PR is the radiated energy. So if the antenna is electrically small, so then its radiation in density, or you can say that its stored density or the power will be reduced somewhere. So energy stored will be increased and the radiated one will be decreased, and hence the quality factor will be increased. For an antenna, because it is a radiating device, so the P radiated should be more as compared to the stored energy in terms of the electric or the magnetic stored energy, or electric or the magnetic charge. Or so if the P radiated is reduced, so the quality factor will increase, and hence the efficiency and other factor will also be reduced. Now, if you will see that how this quality factor, this was the quality factor that was related with antenna stored and the radiated energy, and this is the quality factor that is the related with, you can say, this is the Macklin, this equation was taken from the Macklin, and it is the limit, fundamental limit of the electrically small antenna, that relates that the quality factor is inversely proportional to the maximum linear dimension of your dipole antenna. Let's say if it is Q. So if the KR is the maximum linear dimension of the antenna, where R is the radius of a arbitrary sphere that is enclosing this particular antenna, so R is somewhere nothing but the maximum linear dimension of your antenna. So R is the radius of this arbitrary sphere. It is not physically present. We are just taking that if the antenna is enclosed within this sphere, so how the quality factor is related with this. So quality factor is related with your maximum linear dimension, inversely proportional to the cube of that. So if the antenna dimension is reduced, your quality factor will increase, and your antenna will lose the radiation. It will, instead of radiating the electromagnetic energy, it will be storing the electromagnetic energy. So from here, one can say that the quality factor is not depending on that what is the geometry of the antenna. It is only depending on the what is the maximum linear dimension of the antenna. So Q is independent to the geometric configuration of the antenna here. So this was the Q, the quality factor, that relates that the antenna becomes a storing element, and hence the radiation efficiency will decrease. Another factor is how this quality factor is related to the bandwidth of the antenna. How this is related with the bandwidth. So the fractional bandwidth of the antenna is inversely proportional to the quality factor. So if the quality factor will increase, your fractional bandwidth will also reduce. So hence each and every factor is somewhere related to each other. So quality factor, if it will increase, so it will lose, the antenna will lose radiation performance as well as it loses its bandwidth. So there is another option. If you will see from here, that bandwidth can only be improved if the antenna utilize the maximum available space within this arbitrary sphere. As you know that the maximum linear dimension is R. So if someone is able to increase the volume of the antenna within this sphere, so one can enhance the bandwidth, and this can be seen from the number of the research you can somewhere find. So this is the particular graph that is relating the maximum linear dimension with the quality factor, and there are the number of the efficiency curve. There are the number of the efficiency curve. So you can see this is the 5% efficiency curve, this is the 10%, 50%, and this is ECD. It is the radiation efficiency. We are not talking about the reflection mismatch efficiency, that is ER. We are talking about the radiation efficiency. So not the total one. So if the radiation efficiency curve is 100%, and we are talking that there is a fully matched antenna, we are not considering the reflection mismatch here. So the different antenna, this is also a dipole, this is also the some other dipole, and this is the Gobau antenna. So you can find that this Gobau antenna is approaching towards the 100% efficiency curve. So one can find that the Gobau antenna will be giving you the better efficiency as well as the bandwidth also. So you can see from here that Gobau antenna fractional bandwidth is also higher than the dipole enclosed within the same radius of the sphere. You can see here if you can see here if your antenna is enclosed within this arbitrary sphere of radius r, and if you are able to design an antenna that is utilizing the maximum linear dimension, that is same, but the space is efficiently utilized. So one can see that the Gobau antenna, this is the Gobau, its maximum linear dimension is same. It is the multi-element. It is maximally utilizing the space within the sphere, and hence the efficiency is increased, and hence the fractional bandwidth is also increased. So this can also be analyzed with this comparison, that the classical narrow bandwidth antenna is normally a dipole one. If you are having a biconical one, then it will be giving you an intermediate bandwidth. And if you are having again some tapered dipole, so then you will be having an intermediate. But if you are having a hemispherical dipole, so you can see from here that it is maximally utilizing the geometrical configuration or the available space within the this sphere. So it is giving you a wide bandwidth. The size is same. Each and every antenna is having a same size, but three-dimensional space is somewhere different, you can say. This is valid for your monopole configurations also, where the second pole is replaced with the ground plane. So you will be seeing that the hemispherical configuration will be giving you a wide bandwidth. So this is how a antenna can have the same dimension with an improved performance, you can say. If someone is doing the miniaturization, then these factors should be considered. Another antenna configuration can meet the requirement of utilizing the maximum space with the help of the mathematical equations, and those are fractal equations, you can say. The fractal means the self-repetitive geometries. These are, so if you will see that Koch dipole here, this is the Koch fractal dipole, this is the fractal tree dipole, this is the 3D fractal tree dipole. So all these are utilizing the fractal geometry. So if you will see, this is a simple dipole having the maximum linear dimension same as the iteration 5. But if you will open it, so the current will take the longer path to reach from the one edge to the another edge, and hence it will take the more time, or it will be reducing the frequency. Or you can say if the frequency is reduced, the operating frequency of the antenna is reduced, then the antenna will be working for a huge, you can say, the wavelength, but the wavelength of the antenna is fixed. It is same for each and every antenna. So one can say if you will design for this particular wavelength the antenna, then it will be of the huge size, but it is of the fixed size, so it is miniaturized one. If you are still having some confusion with the miniaturization, you can ask in between also. The fractal tree, it is also utilizing the space, and hence the resonant frequency will reduce, and you can say that antenna is miniaturized. The 3D fractal tree is effectively utilizing the three-dimensional space, and hence the bandwidth is improved as well as the miniaturization is also achieved. So this was just some basic regarding that what is the fundamental limit, how the performance is affected if the someone is reducing the dimension. Now these are the some research articles, those are available in the literature, and giving you the different techniques for the antenna miniaturization. I have included a major portion of the techniques. However, if the some techniques is not available, we can discuss that also. So loading the antenna with the high dielectric constant material, lumped element, line slots. What is this? You can miniaturize the antenna with the help of loading the antenna with high dielectric constant material. As you know that a antenna, if we are talking about, let's say, the microstrip antenna, its resonance frequency is inversely proportional to under the root of, you can say, epsilon r, relative permittivity of your dielectric material used here somewhere. Can you repeat how the miniaturization is done? So better to ask, as I will not be able to see your this message. So if you can ask directly through by just running on your mic, then it will be good. How the miniaturization is achieved, you are asking for. So I am saying that if you are designing, let's say, for 2.4 gigahertz antenna, let's say you are designing for 2.4 gigahertz antenna. So for 2.4 gigahertz, there is some issue with the pointer. So there will be some wavelength, the operating wavelength, that free space wavelength, you can say that, or there will be the guided wavelength, you can say. So this is your guided wavelength. There will be some. If you are fixed with the epsilon r is equal to, let's say, some 4.3, you are designing with the FR4. And you can say your free space wavelength is, let's say, some lambda naught, and your patch size is of, let's say, lambda by 2. You have designed for lambda by 2 your patch, and let's say it is of length L cross W. It is of your patch is of length cross width. So this length is of lambda by 2, half wavelength. So let's say with some techniques, those are available in the literature, somehow you are able to reduce your resonance. Let's say it is of, don't consider this thing because it is coming directly when I am just writing it. There is some issue with, I think, some pointer. So let's say it is of 2.4. It is resonating initially. And with some techniques, you are somewhere able to reduce this resonance to somewhere here. Let's say it is the 2 gigahertz. 400 megahertz downshift you have achieved. So at 2 gigahertz, you have not changed your length of the dipole, or you can say you have not changed your length of the antenna. It is fixed, the dimension. Let's say it is of 5 centimeter or the 4 centimeter. It is same. Physically, it is same. However, with some techniques, you are able to reduce the resonance to 2 gigahertz. So if at 2 gigahertz, the conventional lambda by 2 dipole is designed, or lambda by 2 antenna is designed, so it will be of some higher dimension. It will not be the 4 centimeter, or it will be of some 5 centimeter or 4.5 centimeter. So one can say, if you are able to reduce the resonance to a down with a lower frequency, or you are able to shift your resonance to a lower frequency, then one can say this antenna is miniaturized if you have not changed the dimension. The conventional, the dominant mode resonance, let's say it is coming somewhere here, and somewhere you are able to get the resonance with the same performance parameter somewhere here. So one can say this antenna is miniaturized. Because if you will design at 2 gigahertz, the conventional one, it will be of higher size or bigger size. I hope it is clear to you. So if I will talk about that reduction in the resonance frequency, it means there is a miniaturization. So loading the antenna with high dielectric constant material, as you know that resonant frequency is inversely proportional to your root of dielectric constant. If someone is able to reduce the frequency, one can say it is miniaturized. So if the dielectric constant is increased, your resonant frequency will decrease. So one can say if you are using a high dielectric material, you can miniaturize the antenna. But there will be the problem with this technique. As you will increase the high dielectric, you will replace the high dielectric constant, you will be having the storage of the electrical energy. The electric charge will be stored more, or you can say that your material or your antenna will become more capacitive and it will be losing its radiation. So the reactive part will be more and it will not be behaving like a radiative element, it will be behaving like an storing element. So this will be the problem with the high dielectric constant material.
Sir,
Hanji.
sir, can you just repeat about this high dielectric constant material when you're loading? What exactly happened? Just now you said about increasing the capacitance and so on.
The thing is, your resonant frequency is inversely proportional to the dielectric, relative dielectric constant. The dielectric constant, the unit of dielectric constant, if you will see, it is nothing but it is your farad per meter. No? It is farad per meter, relative dielectric constant, जिसको हम permittivity बोलते हैं. तो permittivity is capacitivity of the material. Capacitivity means that how much the charge, electric charge, it can store. So if you will resemble this antenna as an 2 parallel plate capacitor, if you will, and here there is some dielectric, you can say, in between. So if it is some dielectric, so your capacitivity C is equal to epsilon A by D, the capacitivity of the material. It is depending on epsilon. If your plate and the distance between the plate is fixed, only you are changing the epsilon. So your patch antenna is nothing but it is also looking like the two plates, two parallel plates, once this one and this one, and they are sandwiched like that. You are having a dielectric in between. So if you are having this type of the condition, so you one can say that if the dielectric constant is increased, the capacitivity of the material is increased, and capacitance and inductance are nothing but they are the reactive portion of your impedance. So it is storing more electric charge if you are increasing the dielectric. But for the antenna, at the resonance, you need that the antenna should radiate the electromagnetic energy into the free space instead of storing the energy at the resonance. The reactive part should be zero ideally. So this will be the problem when you will be increasing with high dielectric material. When the high dielectric is used, your antenna will be storing the more electric charge and it will be losing the radiation performance, or you can say it will be reducing the radiation efficiency of the antenna. And if the radiation efficiency is reduced, the gain will also drop, because you know that the gain and directivity are related with the efficiency. The directivity into efficiency is nothing but your gain. So if your efficiency is reduced, your gain will also reduce. I think I am just listening the one sound that is coming with someone is raising some hand. Anu, you can ask. Are you having some question, or by mistake you have just raised your hand? Anu Muhammad.
Sorry, sir. It was by mistake, sir.
So this was done, and now the lumped elements. If you are loading your antenna with the lumped element like L and C or something, so it is also related with the same theory that if the lumped elements are loaded, and you can say that your frequency is inversely proportional to the under root of LC. So one can say that if the L and C are increased somewhere, the below the resonance, if the inductive and capacitive things are increased, so one can say that the resonant frequency will reduce. But due to the reactive portions of these elements, you will be losing the performance. If you are having the lines and slots, means you are loading your antenna with some slots or slitting or something, so then the radiation performance will also decrease, and the antenna miniaturization can be achieved. So if you are doing the slotting, let's say this is the patch, this green portion is the patch, and is your current arrow, current distribution, you can see. So if you are just doing the slotting, so your current will take the longer path around your slot to reach to the another radiating edge, from the one radiating edge to the another radiating edge. So the longer path will lead to the longer time, will lead to the reduction in the resonant frequency of the antenna. Below the resonance, there will be the creation of the resonance or shifting of the resonance that will lead to the miniaturization. As I told you, if there is a shift in the resonance, it will lead to the miniaturization. If you have not changed the original size of your patch antenna or your antenna. So, but there will be the problem that around this slot, due to the image theory, there will be the creation of the cross polarization, as well as there will be due to this image, due to this slot, there will be the creation of I square R losses, and the inductive and capacitive behavior will also come into the picture, and hence you will be having the reduction in the antenna performance somewhere. So these are the some techniques loading the antenna. Another technique, the combination of the techniques can be your patch folding, your inverted F, your shorting pin and plates, or the ground plane. So patch folding means, as you know, that your antenna is made up with the help of let's say it is the patch and it is the ground plane. So if someone is able to reduce its size by just folding this structure, folding this structure means including your patch as well as your ground plane. If you are able to fold it like this paper, if there is some paper and someone is able to fold it like this, so one can say that it is the half of its physical dimension. But there will be the cross polarization level enhancement due to this folding effect. And likewise, the inverted F antenna, if you are able to have the patch folding like this and someone is able to do this, so again you will be having the some cross polarization, as well as if you are having the shorting pin and post somewhere here. So due to this multiple bounce between the ground and your patch, there will be the cross polarization level that will degrade the radiation performance somewhere. So some problems will be there. However, your miniaturization can be achieved. Then another technique is back-to-back patch. You know that the antenna size is limited because of its ground plane. So if the ground plane is replaced with another patch, you can have the reduction in the dimension of your overall dimension of your antenna. But it will lead to the bidirectional radiation, and you will be having a omnidirectional type of the radiation pattern, you can say. The another technique is meandering fractal geometry, arbitrary shape antenna using some optimization algorithm. So meandering means physically the size of the antenna is looking like that it is of lambda by 2. But electrically, the size is increased by just mindering the antenna structure. Likewise, the fractal, I have already explained. The arbitrary shape antenna means you have just taken some algorithm and where you have just kept like my fitness functions are to be like I have to design the antenna with this much of the efficiency, with this much of the gain, and the overall size should be this much. The optimized geometry should be this much. So it will be giving you. So that will be the optimization algorithm. Now, loading the antenna with artificial material like metamaterial. So this artificial material can be your electromagnetic band gap structure. It can be your magnetodielectric material. It can be your reactive impedance or EMC, artificial magnetic conductor surfaces. So depending on the different type of the metamaterial, you can have the different physics behind it, that how the miniaturization can be achieved. So in some techniques, you are just loading the antenna with the inductive capacitive behavior of some metamaterial so that it can compensate with the capacitive inductive behavior below the resonance, and hence the resonance is shifted to the lower frequency. In some techniques, you can have the reduction in the velocity of the propagation of the wave, means slow wave creation you can have, and with that slow wave creation you can reduce the antenna resonance at a lower frequency, or you can say you can shift your resonance to a lower one where the antenna is having the your lower velocity, or you can say the slow wave is there. And other metamaterial can also be there, like you can have the your magnetodielectric metasurfaces, where instead of increasing your dielectric constant, you are just increasing your permeability of the material. So we will be discussing in the some later slide those techniques. So I think we are having a close up at 1:15. So I will be just briefly discussing all these basic techniques of the slotting and slitting and patch folding, and then I will be moving towards the some techniques. Those are based on the metamaterial. So this is the one antenna that is coming from the researchers, IEEE transaction. It is they are reducing. This is the simple, you can say, the geometry and technique that is reducing the size of the antenna by just doing the slots and slitting. So it is just to increase the current path, and hence the miniaturization is achieved. If someone is still having the confusion that how the slitting and slotting or other techniques are giving you the lower resonances, you can ask. The material used is Rogers here. So frequency is now this antenna is at 1.36 gigahertz, and but due to the slotting and slitting, the gain is reduced because of the concentration of the energy or the radiation, and that is stored within these slots, and due to which the gain is reduced to minus 5.2 dBi. However, a 47% shift in the resonance is achieved. So these type of the antennas can be used where the gain is reduced. So one can say that negative gain, what is the meaning of it, how it will be finding some application. There are the applications, those are requiring a negative gain, means you don't need too much of the radiation, too much of the power you don't need. You need a low power. So in the shielded microwave imaging, you can use this type of the array and you can find the application of it. Like the patch folding and inverted F antenna, where the folding is done to achieve the lowered size of the patch, and these folded portion is there, and these are the shorting pins. So due to which the field electromagnetic wave will be bouncing back and forth between the patch and the ground plane. Once it will be reaching to the half wavelength, and then there will be the radiation. So due to the uneven structure and these folding, you will be having the cross polarization radiation. This gain is again having a range from the -1 to 8.25 25 dB in the broad frequency range. This is the broadband structure because of the number of the resonances are created with this E shape of the geometry. The 36.93% of the miniaturization is achieved by just folding and shorting pin method here. This is the one another fractalized geometry based antenna where the some fractalization is used and some slotting is also used so that the current will be taking the longer path here, and hence the miniaturization is achieved. The gain is 5.5 dB. It is a circularly polarized antenna, and that is why they are giving with the dBIC. So dBIC, if you will reduce from the minus 3, if you will do from here, so it will be of 2.5 something dB is the real gain of this antenna. So the miniaturization is not mentioned here, but they are just giving that it is a miniaturized. Obviously, it will be the miniaturized as compared to a normal square or the nearly square patch. Loading the antenna with the meta material, it is with the some meta material they have loaded this antenna. So they have used some DNG and MNG double negative and double positive meta material at the different frequencies. Here, the shorting pins method is used to create the enhancement in the equivalent LNC, and hence the resonance is downshifted here. But at the lower resonance, the frequency, the gain is of minus 2 dB, and at the higher one, it is the 4 dB. It is not coming from the microbe, it is from some other group. The miniaturization is 36.4% compared to the normal folded monopole antenna. It is a monopole antenna. So these were the some techniques. This is the another technique. It is coming from the our group only, that this particular antenna is miniaturized by just cutting the antenna into the half and scaling down this antenna. So this particular antenna you can find somewhere here. This is just half and scaled version of the antenna. So as you know that it is a monopole slotted antenna. So by bisecting this antenna from its symmetric plane where the electric field is symmetric and the magnetic field is asymmetric, or by creating the open boundary or the PMC boundary somewhere here, you will be able to get the similar type of the behavior from the both the antenna. You can find somewhere here the similar current distribution and the electric field distribution you will be finding. So electric field here, if you will see that the figure number 1 is the electric field. So electric field is symmetrical this side and that side. However, the magnetic field is asymmetric. So this is known as your symmetric boundary, one can say. So if one is able to cut this antenna at this boundary, it will be giving you the same behavior. So this is the response of the reference antenna and the bisected antenna. The bisected antenna is giving you the similar behavior, but the resonance is little bit downshifted. So one can say it is miniaturized. One is because of the half is the size of the antenna. One is because the radiation is now coming at the lower frequency also. So if someone is able to have the
Sir,
yes.
Sir, actually, there's one reference antenna and a bisected antenna. Bisected shows like there is a change of geometry. Is there any technical reason why they have to keep this shape only, or in this region only?
In the monopole structure, it is having a, if you will cut into the half, it will be from the symmetric boundary condition only. There your electric field is symmetrical about this axis. If you will be able to see here, the electric field is symmetric. जैसा इधर है वैसा ही इधर है ना, it is same. So from this boundary only you can cut the antenna to get the similar behavior, and the current distribution is also same both sides. So this is the,
As it is monopole, you will also look into the symmetric distribution of E field, and that's how there
you
we
have
will
to
identically keep it.
you have to cut the antenna from the its symmetric boundary, and here the symmetric boundary is coming along the you can say that YZ plane. So this is the YZ plane, and that is why it is just bisected in this plane. So
Okay, sir.
now as the resonance is coming at the lower frequency, so if someone is able to reduce the size of the antenna, again, the down scaling of the antenna, this resonance can be upshifted. Obviously, if the size of the antenna is reduced, then the resonance will shift to the higher frequency to match the original reference antenna. So we are doing the same thing we have done with this scaling, and the antenna is just having the first resonance overlapping with the your reference antenna. However, there is another creation of the mode due to the enhancement in the some horizontal and vertical current component. So this is the impedance curve. I am not going into the depth of that how the measurement and simulations are carried out. That the gain and the frequency, that how the gain and the frequencies are taking place there. These are the radiation pattern. All are the monopole like radiation pattern at different frequencies. And this is the comparison with the present work with the literature. All the tables and things are coming from the research articles only. So you can see that a 75.5% miniaturization is achieved. Present antenna is achieving this much of the miniaturization with a gain of this much, and the efficiency is this much, and all are because of the monopole structure. If it is not a monopole, then you will not be getting this much of the performance. Again, the one antenna that is circularly polarized also, it is similar to the slitting and slotting technique. The slotting is done to create the longer path around the slot. You can see here the current. Initially, the current is moving in the straight path. When you are just slotting the antenna, you are just slotting or slitting the antenna. So then it will be current is taking the different path around the slots. So as you increase the slots size, you will be having the shift in the resonance. You can see from this picture. You can see this is the original resonance. When the slot is only this much of size, so resonance is downshifted a little bit. When you are increasing the length of the slot, then again it is of this much. It is in the MOTL, I think so, this publication. And when you have again increased the slot, you are having this much. These are the select sectoral slits we have just cut it into the this circular patch. So the resonance is downshifted from somewhere 2.45 something to the 1.8. So you can find that this antenna is miniaturized. The circular polarization is achieved by just creating the asymmetricity along the two axes, so that the two degenerate mode with the quadrature time phase shift can be generated, and the circular polarization is achieved. So this is not our interest here. So these are the performances. I am just moving fast because I have already explained this slotting and slitting technique. So this is the same thing, that slotting and slitting, the current is moving, and this is the fabricated prototype, and this is giving you the similar type of the miniaturization. Now come to the miniaturization with the metamaterial. So here the miniaturization of the antenna is achieved with the help of the reactive impedance surface substrate. So you can see from here, the initial miniaturization is just achieved by slotting the antenna. L-shaped slots are created here. So initial miniaturization is achieved. You can see somewhere here. This is the traditional antenna without any slot, simple patch. This is by just slotting the antenna, the current is taking the longer path to reach from the one radiating edge to the another one, and hence the antenna is from this resonance, it is coming to this resonance. Then the further miniaturization is achieved by loading this antenna with this layer, and this is known as reactive impedance surface RIS layer. So what is the benefit of this layer? So as you see here, the RIS layer, when it is excited, the unit cell is excited, so it will be giving you a reflection phase of 0 degree at the resonance, where it is giving you the PMC behavior, perfect magnetic conductor. Below this resonance, it is giving you PEC, the perfect electric conductor, or inductive behavior. And above the resonance, it is giving you the perfect electric conductor, or you can say it is giving you the capacitive behavior. And your antenna is somewhere here, 2.5, where it is inductive. And your antenna, if you will see below the resonance, is capacitive somewhere here. So to compensate the capacitance with the inductive behavior of this race, the resonance can be shifted to the lower frequency, and your antenna is matched at this frequency because of inductive behavior of the reactive impedance surface. So this inductive behavior will compensate the capacitive behavior below the resonance, and a resonance is shifted to the lower frequency, and hence the antenna is miniaturized, one can say. So with this, you can see somewhere here that with a band slot antenna, is efficiency is reduced. Again, the efficiency is reduced. Efficiency is reduced because of the accumulation of the charge within the structure. The gain is also reduced, but the miniaturization is achieved. And how much the miniaturization? 53% of the miniaturization is achieved by a compensation of your gain and the bandwidth as well as your efficiency. So each and everything is coming with the loss of another thing, you can say. You have to compromise somewhere. Now, another technique is the miniaturized curved slotted antenna with fractalized EBG. The electromagnetic band gap structure as an metamaterial is utilized to miniaturize this antenna. So if you will see, the previous structure was having the L slot. Here, the further miniaturization is achieved by just increasing the length of the slot. One can say, why you have just curved in this direction? Why not like you have taken your slot somewhere here in the center? I will not be able to find my feed point if I will do that thing. So that is why it is curved like this. So by curving, again, the conventional and the curved slotted antenna is miniaturized with the slotting slitting techniques, you can say. Further miniaturization is achieved by replacing its ground plane. This is the ground plane. It is replaced with the fractalized uniplanar electromagnetic band gap structure. This is the uniplanar EBG. It is not the mushroom structure. This is the strip line, and this is the L, and one will be giving you the L, and this behavior will be giving you the C, capacitance and inductance. So fractalized uniplanar EBG structure is this. So if you will, this is the unit cell, one unit cell of the structure. So if you will simulate, and you will find that the slow wave factor beta by K naught of this particular unit cell, if you will calculate, and you will find that this is the conventional microstrip line simulated, and the simulated, and you can say that calculated. This is the beta by K naught slow wave phenomena of that. It is in the straight line. Nothing is happening there because it is a transmission line. When you will deal with this fractalized EBG structure, you will find that there is an enhancement in the slow wave because of the prohibition of the electromagnetic energy, or the transmission of is prohibited with the electromagnetic band gap structure. So if this particular band gap is given by, you can say this is a 2.0, and if it is 2.5, after 2.5 gigahertz there is a band gap. So before band gap, what is the meaning of band gap? Means the prohibition of the electromagnetic energy is there. So how the prohibition of the something is achieved? It is not like that if someone is going in this way and you have just a stop. You have to slowly stop your electromagnetic wave. So your electromagnetic wave is, let's say, propagating with some velocity. Slowly it will be, the velocity will be downshifted, you can say, or velocity slow wave factor will increase, so that the velocity of the wave is prohibited and there will not be a propagation within this particular band of frequency. Within this band there is a band gap, but below the band gap, this region is known as slow wave transmission zone, where the wave is propagating but in a slow velocity or low velocity. So this particular region where the slow wave is achieved can be utilized for the miniaturization purpose. As all know that the EVG is used to enhance the gain. We are not using that particular region of the EVG characteristic. We are using the slow wave region here. So in this slow wave region, the velocity is downshifted. I will give you the one example, that if the velocity of the wave is downshifted, and you know that the velocity is somewhere related to your frequency into wavelength, and your wavelength of the antenna is fixed. You have not doing anything with the wavelength, it is fixed. So to maintain the relation, your resonant frequency should be downshifted. So you can see somewhere here, this is the initial one resonance, this is the second resonance. At from 3 to it is coming like a 2.3 somewhere or so. Now again, after using the EVG, now the resonance is at 1.5 something. How much decrements? Around 1.5 gigahertz of the shift is achieved from the conventional antenna. So this particular antenna is giving you 74.76% of the miniaturization with a efficiency. There is no decrement in the efficiency, not that much, you can say. With the FR4 substrate, 81.59% of the efficiency is achieved. However, there is a decrement in the gain, but efficiency is not decreased because of the, you can see it is behaving like a monopole now. Why monopole? Because of slotted, or you can say that defective ground. You have replaced your conventional ground with this ground that is having the perforation. So you will be having the bidirectional radiation pattern. You can see this is the black one is the conventional antenna, conventional microstrip, and this is the back lobe of the conventional, very small one, you can say. And now the EVG one is having your monopole type radiation pattern, figure of 8 and a circle in the H plane. So these are the some limitations. Another very interesting metamaterial structure is artificial planar magnetodielectric metasubstrate. This is the first proposal work done in our laboratory. These all the work are done with our group. So this is the first proposal that practically realized the nearly matched impedance magnetodielectric metasubstrate. This is the first proposal that was practically realized. So how this miniaturization is achieved? As you know that frequency is inversely proportional to the refractive index, and refractive index is proportional to the epsilon and mu. Epsilon drawback I have already discussed, that if you will increase the epsilon, you will lose the radiation. But another method is you can, but if you are able to increase the refractive index, you will be able to reduce the resonance frequency, or you can say the miniaturization is achieved. Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, yes.
So if N is
Yes, sir.
increased, your resonance frequency is reduced. So for a given miniaturization factor, if someone is saying that I want this N to reduce this much in the F, one can enhance or one can achieve the miniaturization by, instead of increasing epsilon, you can increase mu. But the problem is you are not naturally having the high permeability materials. So you have to engineer that, and that is dispersive permeability function must be realized to do though. So how to achieve it? It is achieved with the split ring resonator, complementary split ring resonator, and this particular split ring resonator is formed like that. You are having your planar structure, means through the via you have created your split rings such that they can be excited with the electric and magnetic field or with the magnetic field of your antenna only. So as you know that this is the split ring, complementary one, and it is excited with the magnetic field that is perpendicular to the axis of your ring. Oh, sorry, it is parallel to the axis of the ring, or the surface, it is perpendicular to the surface of the ring. So if it is a ring and the magnetic field is perpendicular to it, so it can excite your current somewhere in the field, in the ring. So it will excite a current, and that current will lead to the creation of the magnetic dipole moment in this, and that will change the permeability of the material, you can say. So if the magnetic field of your patch antenna is, let's say, in this direction, and you are placing your antenna in this such that the magnetic field is perpendicular to it, so you will be able to miniaturize. But what should be the dimension and all the things you have to consider. So we have created a nearly matched magnetodielectric substrate. Near to matched means where epsilon and mu both are of the equal value. So we have extracted the metamaterial parameter with the help of the real and imaginary S11 and S21. So this is the permeability and impermeability function. So at 2.35 gigahertz resonance of your antenna, you are having, let's say, 3.95 epsilon r and 3.93, approximately the same. The behavior is achieved with the epsilon and mu. Both are of same. If the epsilon and mu are same, the refractive index is also the same, and your characteristic impedance will be matching to the free space impedance, because you know that eta is equal to eta naught under the root mu over epsilon. So if both are same, it will be cancelling each other, and you will be having nearly matched impedance metamaterial, and that will be able to match the free space impedance, and you will be having easy of matching, and the miniaturization can be achieved because you have increased your mu also. So these are the theoretical background that how the resonance is depending on epsilon and mu, and how the effective dielectric is calculated. And these are the some case study with the number of the different type of the structure. The like one structure is the proposed one, the first one, magnetodispersive metamaterial, which is changing with the frequency, all our frequency. This is the non-dispersive. The same metamaterial parameter like epsilon and mu is achieved with the epsilon at 2.39, 3.95 and 3.93 is fixed at a particular frequency, and the loss tangent is also fixed. Third is hypothetical. All are the hypothetical material. Hypothetical non-dispersive lossy dielectric substrate means the dielectric is non-dispersive, but it is a hypothetical, means epsilon r is only there and there is no mu. So it is achieved with the multiplication of these two. You are considering that the mu r is 1. So it is of 15.52 value is your epsilon, and the loss tangent is taken. Magnetic loss tangent we have not taken here because it is a non-dispersive dielectric. Then hypothetical non-dispersive loss-free, where the loss tangent is are 0, and the rest is your the same value of epsilon r with Rogers. So all these different substrates are compared. Obviously, the designed one will be giving you the lower efficiency. However, at the Rogers and the hypothetical material will be giving you the higher efficiency because of the dispersive nature of the designed material. You will be losing the performance, but it is giving you a idea that how the miniaturization can be achieved with the dispersive material, magnetodielectric material. This is the fabricated prototype. It is very small. You can see that 4.5 centimeter cross 4.5 centimeter is the overall dimension. However, only the 2.5 centimeter is your length of your metamaterial structure, that is between these two layers. You can see the impression because it is sandwiched in this layer. These are the shouldering. So I'm not going into the depth of that how the fabrication was done. So this is the first proposal to the best of author's knowledge that was proposed at that time. Now this is the what are the potential and limitation as the time is approaching to 1:15. So this is the comparison of the different techniques. So there are some limitation and the challenges. Potential are that how much the percentage of the miniaturization is achieved. So like slotting and downscaling will be giving you the uneven structure, and it will be decrement in the gain due to the lower frequency due to the uneven structure and the cross polarizations. Sectoral slits is also giving you the performance, but that is limited with the length of the slits. Like with the fractal boundary structure, the limitation is same. With the RIS, you are having the effect of the radiation characteristic, and the layered antenna geometry is there. With the EBG, you are having the bidirectional radiation pattern is the limitation. If one is asking for only unidirectional one, then there will be the issue. And increment in the back lobe level is also high for this. With magnetodielectric metasubstrate, the bandwidth is limited because of the dispersive nature, and layered geometry. It is also not the simple single layer geometry. So this is the theoretical limit, where you can see that this is the single band and dual band theoretical limit that lies with the logarithm scale of the dimension of the antenna Ka, where the K is the wave number and the A is the maximum linear dimension of the antenna, and this is the beta n, the bandwidth and efficiency product. So whether all these designed are over the theoretical limit, or they are approaching toward the limit, or they are diverting somewhere from the line. So you can see that design 5 is approaching towards the some designs are not available in this particular slide. I have not included because of the time limitation, but design 5, which is I think it is with the EBG one, so it is matching with the bandwidth and efficiency curve. So this is the comparison with the theoretical limit and the design. So the conclusion is that all the techniques are giving you the miniaturization and finding the some application depending on their performances. But one can say at the conclusion that it is a art of compromise between your miniaturization and the performance. Means it is up to you that what is your requirement and which techniques will be helpful to you in your application, and you can choose wisely according to that. Thank you. I think time is 5 minutes more I have taken. You can ask if there is some query. If there is no query, then we can close this lecture.
Sir,
Yeah.
excuse me. Sir, I want to know what are the key factors to consider while selecting a type of a metamaterial for a specific antenna application, like wireless communication or IoT kind of
So this
applications.
is not the like wireless communication IoT. You have to ask yourself and the literature that what
Mhm.
are the different you can say that requirements, like what is the requirement of your gain, what is the requirement of your efficiency,
Mm.
what is the requirement of polarization, what is the requirement of the beam width, what is the requirement of your radiation pattern. So all need to be considered, that what are your requirement and whether a particular technique will find the solution to your requirement or not. Like if someone is asking that I need a unidirectional radiation pattern only, so
Mhm.
obviously he or she cannot do the perforation in his or her ground plane. So the technique is accordingly chosen depending on your requirement. That what is your uh, antenna characteristic requirement?
Okay. Okay, sir. Thank you.
Is there any other question?
No, sir. Thank you. Thank you so much, sir,
Thank you.
for explaining all the things in very sufficient and in a simple way.
Okay, thank you so much for all. So today's lecture series is completed. We will be meeting tomorrow at 11 a.m. sharp. So I will request all the participants to join 10 minutes before, so that the external expert will start at the 11 a.m. sharp. Okay, thank you so much. You can leave this talk.
Thank you, sir.